Welcome back. Mr. Sutton here with the BC Calculus 518 Part 2 homework solutions on improper integrals. For this problem, if R is the unbounded region between the graph of this function and the x-axis for x greater than or equal to 3, then what is the area of R? So here you have to realize that they're asking for an integral because you're trying to find the area between some function and the x-axis. And what are the limits of integration here? Well, they said x greater than or equal to 3. So that means from 3 to infinity. Well, we can't actually have infinity as an upper limit. That would be an improper integral. So instead, we are going to write this as a limit as b approaches infinity of the integral from 3 to b of the original function here. And now we have to go ahead and integrate that, and we'll keep the limit around until we're actually ready to quote-unquote plug in infinity. All right, so since this is a little bit of a mess and I see an inner function whose derivative is somewhere else in the problem, I'm going to try substitution on this. So I'm going to let my u value equal ln of x, and then du is 1 over x dx. And then if I isolate dx, I've got x du. Now I also have to change my limits of integration. So if x equals 3, then u is going to be the ln of 3. And if x equals b, then u is going to be the ln of b. Plugging all that back in, we've got this limit of the integral from ln of 3 to ln of b of, well, now I've replaced ln of x with u, so this is 1 over x times u squared. And then I have, instead of dx, du times x. Simplifying this a little bit, I can cancel out these x's, and I'm going to rewrite this with a negative exponent. So this is going to be, let's see here, u to the negative 2 du, with all of this stuff unchanged. Now it's time for my antiderivative. This bumps up to a negative 1. So I have negative 1 u to the negative 1, evaluated from ln of 3 to ln of b. Still have this limit hanging around. Now it's time to actually plug these things in. So I've got, and this is really just negative 1 over u, if I write that as a fraction, which I'm going to do now because it's a little more helpful to see it that way when you're evaluating. So I've got negative 1 over ln of b, and then I'm going to have plus 1 over ln of 3. Normally I'd be subtracting, but I've already got a negative u value here. Evaluating this, well, as b goes to infinity, since this is in the denominator, this first term goes to 0. The second term is what it is. Don't really need to simplify it. So that adds up to then 1 over ln of 3, which ends up being choice C. On this problem, we want to know which of the following statements about integral from 0 to pi of secant squared is true. So this is one where if you're not careful, you might just try to take the antiderivative and plug in the limits. It's an easy antiderivative, right? Tan of x. So we've got tan of pi minus tan of 0. Well, that's just 0 minus 0, which you would say, okay, so the area is 0. However, you would actually be wrong on this one. To see why, realize that secant is really 1 over cosine. Cosine of pi over 2, which is in this interval here, is 0. So if you've got 1 over 0 happening when you're evaluating this thing, you might run into some issues. So because of this discontinuity at x equals pi over 2, it's more for the cosine function here, this is an improper integral, and we have to actually evaluate it from the left and the right as we approach pi over 2, instead of just plugging these things into tangent. So I'm going to rewrite this with limits. I've got the limit as we approach b, as b approaches pi over 2 from the left of 0 to b of our function secant squared. And I also have to approach pi over 2 from the right, so I have the limit as a approaches pi over 2 from the right of a to pi secant squared. Now I'm just going to evaluate these separately. So I've got tan of x from 0 to b, still have this limit as b approaches pi over 2 from the left. And over here I've got essentially the same stuff, but with a different limit and different limits of integration. So limit as a approaches pi over 2 from the right, tan of x, a to pi. And we could keep going. We could plug in b and 0 over here. We can plug in pi and a over here. You actually don't have to keep going because at some point you are going to have to plug b into here and actually find the limit as b approaches pi over 2 from the left of tan of b. Now let's think about what's happening here. Maybe you remember the graph of tangent, right, which looks kind of like just the cubic function over and over again. And you might remember there's a vertical asymptote at pi over 2. So that's going to give you some kind of infinity. Now, if you didn't remember the graph of tan, and this was a no calculator question, so you needed to remember it to do that, you could also think of tan as the slope of an angle on the unit circle. As your angle gets closer and closer and closer to 90 degrees, pi over 2, your slope is getting closer and closer to being a vertical line, which is an undefined infinite slope. So any way you slice it, this comes out to infinity. Since we have an infinity for this part of the limit, that means this whole integral is going to diverge. So now the million-dollar question is, which of these answer choices, C or D, should we pick? Are we diverging because the limit as x approached pi over 2 from the left of secant squared didn't exist, or because it didn't exist for tan? It actually ends up being D. It's this limit here that proves that this diverges. The original function by itself doesn't prove anything. You have to look at the antiderivative and the limits for that. So choice D. For this problem, we're trying to find the integral from 0 to 1 of this rational function. Now, just to be on the safe side, I'm going to factor this to see if there's any discontinuities from 0 to 1. And if I factor this, I have x minus 1 and x plus 3 in that denominator. And we see that there is indeed a discontinuity at x equals 1, which is going to affect our integral here. So because of that discontinuity, this is an improper integral, and we have to actually rewrite this as a limit and go from there. So I'm going to write this as the limit and I'll call this b, as b approaches 1 from the left side of the integral from 0 to b of that rational function. And now I have to actually integrate it. Now there's two ways to do this, using substitution and using partial fractions. On this slide, I'm going to show you substitution, and if you want to see the partial fraction solution, then just keep watching the video for the alternate solution. But using substitution first, so I see here that I have something with an x squared and something with an x. I'm thinking, well, there's at least a chance if I take the derivative of this thing, I might be able to cancel out this x plus 1. So let me let my u value be x squared plus 2x minus 3. It's not a very clean, easy u value, but we'll deal with it. Du then is going to be 2x plus 2 dx. And then isolating dx, I have du over this binomial. Now I have to come up with some u values, and this is where things get a little bit obnoxious. Not so much for 0. I mean, if x equals 0, then u is just going to be negative 3, because everything else zeroes out. But if x equals b, well then we have to basically plug b in for all the x's here, and that's kind of annoying to write as an upper limit of integration. But this is the price we pay for not having to use partial fractions. So going back now and plugging everything in, we're going to have the limit as b approaches 1 from the left of the integral from negative 3 to b squared plus 2b minus 3. So again, kind of annoying as an upper limit, but whatever. And now we have x plus 1 over u. That's kind of nice. And then instead of dx, we've got du over 2x plus 2. But I'm actually going to go ahead and factor this into 2 times x plus 1 because I'm about to cancel out these x plus 1s. So why not? Canceling them out, I get all of this limit stuff and this is going to now be 1/2, because we still had a 2 down here, of 1/2 times u to the negative 1 du. All right. At this point, it's time to actually take an antiderivative, which is going to be 1/2 ln of absolute value of u. We still have the limit as b approaches 1 from the left. We still have the upper and lower limits of integration here. But before I go ahead and plug all this craziness in, we already know that when we plug 1 into this expression, we get 0. So if we're just considering the limit of 1/2 ln of all this stuff as b approaches 1, we're basically asking what happens to ln as we get closer to 0. Well, ln goes to negative infinity. So this is going to be not existing for that limit, which means our integral itself diverges regardless of what happens with this negative 3. So that means we have answer choice E. Now, for those of you who checked out my solution to this problem and didn't do it the way I did it, used partial fractions instead, well, this one's for you. So I still factored this thing, and I realized that I had that discontinuity at x equals 1, so I need to set this up as a limit. Same limit as my other solution. B approaches 1 from the left, 0 to b of all that. But this time I'm going to do my little partial fraction dance. So I'm going to split this up into a over x minus 1 plus b over x plus 3. Then I multiply everything by x minus 1, x plus 3. That leaves me with x plus 1 on the left. And over here, the x plus 1's cancel, so I have a times x plus 3. Over here, the x plus 3's cancel, so I have b times x minus 1. And then, let's see now, I have to plug in some convenient numbers to get rid of a or b, depending on which one I'm solving for. So I'm going to choose the x value 1, because that's going to get rid of b and allow me to solve for the a value. So plugging in an x value of 1, I've got 2 on the left, and on the right, this is a times 1 plus 3, so 4a. b is gone completely because it's just getting multiplied by 0. So that means we have an a value dividing by 4 of 1/2. All right, to solve for the b value, I'm going to choose an x value of negative 3 to plug into this equation. So that gives me negative 2 on the left. On the right, a is gone. I've got b times negative 3 minus 1, so negative 4b. And dividing both sides by negative 4, b also equals 1/2. Okay, coming back to this integral now, I'm going to split up my integrand. I'm going to rewrite this as 1/2 over x minus 1, and I still have all that limit craziness in the beginning. And now I also have plus 1/2 over x plus 3 dx. Going a little bit further, taking my antiderivatives, I've got 1/2 times the ln of absolute value of x minus 1. And I've also got, same thing, 1/2 ln absolute value of x plus 3. Still evaluating from 0 to b. Now, in this case, before I actually plug all this craziness in and try to evaluate it, I notice that if I plug b in here, if I just consider the limit as b approaches 1 from the left of ln of b minus 1, I'm essentially asking what's happening to ln as the stuff inside approaches 0. And again, ln as you approach 0, that's giving you negative infinity. So this does not exist, meaning we have a divergent integral, meaning we have choice E. For this problem, I'm told that the integral from 1 to x of f of t dt equals this stuff, and then I'm asked for the limit from 1 to infinity of f of t dt. Well, we essentially have this integral function that when you plug something in, all this stuff happens to it. And over here, you're essentially trying to plug infinity into that. Well, you can't really plug infinity in. You can only approach it. So we need to rewrite this as the limit as x approaches infinity of all of this stuff here. And if I do that, I'm just essentially going to treat this like a normal limits problem now and see what this comes out to. So I can't really do anything about this 4 just yet, but I can eliminate some lesser terms. So inside the square root, the 4x squared is going to dominate down there. So I'm just going to rewrite this as 20x over radical 4x squared, all of that minus 4. And I know the square root of 4x squared is just 2x. 20x over 2x simplifies to 10. So I've essentially got, and I can get rid of my limit now, I've essentially got a 10 minus 4, which is 6. So choice A. For this problem, we're trying to find the integral from 1 to infinity of this expression. I'm going to need a limit because this is an improper integral with an infinite limit of integration here. So I'm going to take the limit as b approaches infinity of integral from 1 to b of all this stuff. And now that I've written it like that, I actually need to find the antiderivative. I'm going to use substitution here. I've got an inner function whose derivative, or at least a piece of it, is out there somewhere. So I'm going to let my u value equal, we'll say negative x squared. It would also work if you let it equal positive x squared, half a dozen of one, 6 of the other. So then du is going to be negative 2x dx, and then dx is du over negative 2x. Now for the u values, if x equals 1, then we've got a u value of negative 1 squared, or just negative 1. If x equals b, then we've got negative b squared for our u value. Plugging all that back in, we have the limit as b approaches infinity of the integral from now negative 1 to negative b squared of, we've got x times e to the u, and now we've got du over negative 2x replacing the dx. Canceling out those x's, I can write this as the integral of all this stuff of negative 1/2 e to the u du. And let me just change that. There we go. All right. So taking my antiderivative, that's going to be negative 1/2 e to the u, which is pretty convenient, evaluated from negative 1 to negative b squared. Still have b approaching infinity for that limit out there. And now plugging these things in. Actually, I'm going to take out a negative 1/2 in the beginning so I don't have to mess around with it. Now I'm just doing e to the u with these two things plugged in. So I've got e to the negative b squared. I can rewrite that as 1 over e to the positive b squared inside there. And I've also got e to the negative 1, which is 1 over e to the 1, and we're subtracting here. So let's see now. As b approaches infinity, this first term in here, since it's bottom heavy, is going to 0. This other term is just minus 1 over e. So I have negative 1 times 0 minus 1 over e. So this is negative 1/2 times negative 1 over e, which is positive 1 over 2e, which is one of the answer choices, choice B. For this problem, we want the integral from 0 to infinity of this expression. Now, I've got an infinity in my limits of integration. This is an improper integral, so I need to rewrite this using a limit as b approaches infinity of the integral from 0 to b of all that stuff. So now that I'm handling this as a limit to infinity, it's a little bit more mathematically legal. So now I have to actually take my antiderivative for this stuff. I see an inner function here whose derivative is elsewhere in the problem with multiplication. So this seems like a good candidate for u substitution. Now I've got choices here. I could let my u value be negative x cubed or just x cubed, half a dozen of one, 6 of the other. This time around, I chose to let u equal x cubed, but this would have worked out just as well if you let it equal negative x cubed, as long as you're consistent with your negative signs. So using this way of doing it, I've got du equals 3x squared dx, and then we can say dx equals du over 3x squared. So then if x equals 0, u is going to be 0, and if x equals b, u is going to be b cubed. Going back in here now, we've got limit as b approaches infinity of the integral from 0 to b cubed of, now we've got x squared times e to the negative u, and we have a du over 3x squared. X squareds cancel. We've got 1/3 e to the negative u du. And the antiderivative of that is going to be negative 1/3 e to the negative u. Still evaluated from 0 to b cubed. Plug in all that in now. Actually, I'm going to pull out a negative 1/3 just so I don't have to mess around with that inside. So now I've got e to the negative b cubed, which I can write as 1 over e to the b cubed, which is going to be helpful when I actually approach infinity with that b value. And for this other piece, I've got, let's see, e to the negative 0, which is just e to the 0, so really no need to be crazy about this. So you actually could have written this one as e to the 0 or 1 over e to the 0. Doesn't really matter. It's 1 any way you slice it. So now plugging in infinity here, that means I have a bottom-heavy function right here, this 1 over exponent going to infinity. So this goes to 0. We essentially have negative 1/3 times 0 minus 1. So negative 1/3 times negative 1 then, which is positive 1/3, which is choice C. For this problem, we're trying to take the integral from 1 to infinity, so we're going to need a limit as b approaches infinity of integral from 1 to b of this stuff here. And now that we've rewritten it legally, let's actually find the antiderivative. I've got an inner function down here whose derivative, x, is somewhere else in the problem. I'm going to try substitution here with a u value of 1 plus x squared. So du then is going to be 2x dx, and that means I can rewrite dx as du over 2x. Next, my u values. If I have an x value of 1, then I must have a u value of, let's see, 1 plus 1 squared, so 2. And if I have an x value of b, then I have a u value of 1 plus b squared, which is a little bit clunky, but we'll deal with it. Plugging it all back in, I have limit as b approaches infinity of the integral from 2 to 1 plus b squared. Here I've got x over u squared, and then instead of dx, I have du over 2x. So the x's cancel. I've got 1/2 times u to the negative 2 if I rewrite that, so I can use my reverse power rule a little easier. Same limits of integration and same limit out here. So now taking my antiderivative, this bumps up to a -1. We've got -1/2 u to the -1. Still evaluated from 2 to 1 plus b squared. Still have this limit out here. Plugging all that in now. I'm going to take out that -1/2 because that's kind of annoying to look at. And now inside, I'm going to have, let's see, this stuff to the -1 power. So I guess we can write that as 1 over this stuff, 1 plus b squared. And then I've got 2 to the -1, so -1/2 in there. Taking my limit as b approaches infinity, I've got 1 over infinity essentially, so that goes to 0. We essentially have -1/2 times 0 minus 1/2. So -1/2 times -1/2 gives us 1/4, which is choice C. On this problem, they're saying R is the region between the graph of y equals e to the -2x and the x-axis, x greater than or equal to 3. They want the area of R. So for this one, we need essentially an infinite integral from -3 to infinity of this function. That's what our area could possibly be represented as, but we can't really evaluate it that way. That's an improper integral. So instead, we're going to do the limit as b approaches infinity, integral 3 to b of all this stuff. And now to take our antiderivative, this one's actually not so bad. It's essentially e to the -2 divided by -2, so -1/2 times that. And we're evaluating that from 3 to b, again as b approaches infinity. I'm taking out my -1/2. So inside now I've got e to the -2b minus e to the -2 times 3. I'm going to write those in fraction form. So this first one I'm going to write as 1 over e to the 2b. There we go. Minus 1 over e to the 2 times 3. And now as I approach infinity on that b value, this is bottom heavy, so it's going to 0. I've got 0 minus 1 over e to the 6 inside. Still got this -1/2 outside. -1/2 times -1 over e to the 6, that's going to be positive 1 over 2 times e to the 6, which gives me answer choice A.